Hey guys, so welcome back. One thing, I've gotten everyone's homework and I've actually posted the solutions to that homework. You can take a look at that. It's on Blackboard. We're going to have a take-home final. So I'll get that posted sometime next week and it'll be due by the end of finals week, which I guess is May 1st. This is going to basically be a glorified homework assignment, but it gives you guys the chance to work on some a little bit more in-depth problems than say I would give on a normal final. So I think that'll be good. I've done this actually in the past. I think I've given a take-home final at 580. It can go well. Okay, so last time where we left off, we were talking about complex measures. And so now the idea is we've got, when I write this every time in the notes, everything, this is some type of space with the sigma algebra. And then we've got this mu from the sigma algebra. It's a function from the sigma algebra to the complex numbers. And notice the real numbers are a subset of the complex numbers, so you can do what's called real measures. But the point is they can take on positive, negative values, complex values. And the key thing here is that we have this so-called splitting when E is a countable disjoint union of sets in M. The Ek, of course, are in M. Okay? And so this behaves like a measure. And by the way, I've updated the notes. I'm going to add a lot. I've actually added a lot to this section. I got kind of carried away. I'm not going to cover all of it on the videos, but you can take a look at the notes and if you want some more in depth. And it turns out that this actually gets you all of the properties of a measure. The tricky property that you lose when you switch to complex, oh, and by the way, all the properties of a measure. What do I mean by that? Well, if you go back and look at the original proofs of just measures and say the continuity from below, the idea that if you have an increasing sequence of sets, then the limit of the measures is the measure of the union, and likewise a decreasing sequence, etc., etc. There's a few properties that I've included in the notes. Turns out this is all you need, okay? You don't need positivity for that. You just need this kind of conservation of mass, so to speak. But one thing you lose is you lose the monotonicity. Complex measures do not satisfy this when A is contained in B. And both are in M, obviously. They do not. This is what we lose when we switch to complex and real measures. This is a problem. So we got into it last time, but the way we compensated for this is we introduced the total variation measure. And so what we did was we introduced this to be the soup of all. And so somehow what I'm doing here, when I'm taking this, imagine it just being a real number here. Somehow I'm figuring out the partitions where I can get the total amount of mass, positive mass. So these may be, plus or minus, but if I pick that partition right, so here E is a disjoint partition of sets in M. And so the idea here is, the real, think of it as real. The real measure of the set E, well, it may have like some positive part, some portion of E is positive, some portion is negative. Well, if I do this, then what I can do is kind of pick this partition so the EK pick up all the positive ones, and then some of the EK pick up all the negative, and I partition those separately, and I can get this total variation. Last time we proved that this was indeed a measure, and so it may seem kind of strange that this is actually a measure. Why? Because measure needs to satisfy this equality, basically, but we've got soups and absolute values here. Well, the proof's very classical measure theoretic, and so last time mu is a measure. Okay. So this time what we're going to do is actually prove, and I'm going to go kind of quick through this. You can read the notes for the details. But we're actually going to prove that this thing is a finite measure, which is maybe a little bit surprising. So we talked about the consequence of this being a complex number. You always have that, if I take the modulus of that, it's finite, but that this thing's a finite measure is maybe a little bit surprising. And so this uses this funky, oh, and actually before I do that, let's just do a little calculation here. So if I take L1 lambda, where lambda is a positive measure, recall that we have to, use this adjective about positivity because we don't want it to, we'll talk, when I say measures, technically that can mean real, complex, or positive, okay? But if I take a lambda where lambda is a positive measure, and I define a complex measure like this is the important example, then my question is, what does this equal? What is this? How do we describe this measure? Well, this is pretty easy. It turns out that mu is given integration against f. Total variation of mu is, so it turns out this is, of course, the modulus of. And this is really easy to prove. So you can get an inequality one way by looking at the partition where f is positive and negative. And then you can also get another inequality the other way by just pulling the absolute values inside. Try to prove this yourself, and then if not, go to the notes. You can look. I've actually got it worked out there. Okay, so the next thing, remember this is a really, really important example of a complex measure. You integrate a positive measure against the L1 function. So the next thing is this funky little lemma. We're going to say towards, turns out this is a finite measure. So what we've shown so far, this is a positive measure. Turns out it's measured the whole space of the finite measure. Maybe a little surprising. Okay, so we need a little lemma here. And this is what I call a reverse triangle inequality, although you think of the classic reverse triangle inequality as where you get a difference of the absolute values is bounded by the absolute value of the difference. This is just kind of crazy. So given finitely many numbers, complex numbers, there exists a subset of indices. So some subset of these 1 through n, such that on that subset, so normally you pull the absolute values in the sum and you get that is less than or equal to the sum of the absolute values. That's the usual triangle inequalities. Not quite true. We're going to go the other way and actually only on a subset. And this constant is kind of strange, but you'll see where it comes from in the proof. And now this is. And I remember the first time I saw this, I just flat out did not believe it. But it's not too bad. If you do these with real numbers, this is significantly less complicated. Basically, to do this, you just do, I think you'd be able to get a half here. Yeah, a half. And you just look at the z's that are positive and negative. But that being said, this is for complex numbers. And I remember when I first saw this, I didn't believe it because you've got like this reverse triangle inequality, but the constant makes up for everything. And so here's the proof of this. Oh, by the way, this constant here, this is a result of my techniques, which I learned from this class in grad school. Best constant you can put here, believe it or not, is 1 over pi. And so that makes the inequality a little bit better. And if you read through Rudin, he's got a proof with the 1 over pi. He doesn't have a proof that it's the best you can get. Okay, so here's the idea of this, so proof. So first thing, we can assume all these are non-zero numbers. Okay, so zk is not 0 for all k. From 1 to n. And that's because if I have 0, it's not going to contribute to either side of this equation. Okay, then what we're going to do is we're going to take and we're going to divide the complex plane by, so you can think of the complex numbers as real and imaginary parts, and you can think of them on the plane. This is the real axis, this is the imaginary axis, so we're going to divide it by imaginary equals plus or minus real, or if you're thinking about the complex numbers as x plus iy, y equals plus minus x. And so we'll do this. And we're going to divide that complex, so this is right here, this is real equals imaginary, and this is real equals minus imaginary. Okay. We're going to divide, so instead of doing the usual quadrants, we're going to divide this into 4 quadrants. Okay, so there's my 4 quadrants. And so the point is that there exists a quadrant, there exists, say, qk, for some k 1 through 4, such that, let me write j here, zj in qk, zj, that this is greater than or equal to 1/4 times the sum of all of them. Let me write j here too. Why is that? Well, otherwise, if there did not exist, that would mean this inequality would go the opposite way for all 4 quadrants, and that inequality would actually imply that these things are, that would imply that this is strictly less than itself, and that can't happen for non-zero numbers. So there exists one quadrant, and without loss of generality, we can assume that quadrant is Q1. Assume it's Q1. Why is that? Well, this is where they get a little bit tricky. So the idea here is I've got my points Z kind of scattered all around here, right? And there's one of these quadrants, maybe these points satisfy this. Well, then what I can do is I can rotate those points over into Q1. So I can basically rotate this whole picture. For instance, if it were Q3 that indeed satisfied that, then I could take and multiply all the Z by e to the pi I. If I did that, it would it would rotate all of these and would move the points in Q3 to Q1. Q1 would go to Q3, Q2 would go to Q4. And now why can it do that? Well, if you look here, if I multiply, I can stick an EI, any theta in these, and the absolute values swallow it up. Why? Because I can factor that out. So the moral of the story is I can assume that it's Q1 that satisfies this. All right, so let's go from there. Let S equal a set of indices such that ZK is in Q1. Okay, now what's so special about Q1? Well, let's take a look here. Here's Q1. Didn't quite draw that right. Okay? If I take any z in Q1, let's take a z in Q1, I can write that z as e to the I theta, where theta lives between pi over 4 and negative pi over 4. Right? Here's negative pi over 4, here's pi over 4. And if you write out what this is equal to, this is cosine theta, this is Euler's formula, sine theta, and in particular, this is the real part of such a z in here, this real part of z. And because theta is in between negative pi over 4 and pi over 4, cosine is greater than 1 over root 2. And so there's where that root 2 comes from. Okay? Right? And just draw this out. Cosine of theta. You draw out the cosine function. Here it is. And if I restrict that theta to negative pi over 4 and pi over 4, look up here. Cosine's always above the line 1 over root 2 or root 2 over 2. Okay? All right. Now we're ready to roll. So, how do we do this? Well, we have K and S, ZK. Well, this is certainly greater than the real part. K and S, ZK. Okay, and that's equal to real part of the sum of a bunch of numbers is the sum of the real parts. And now, this inequality, these guys live in Q1, this inequality says that this is greater than ZK, and the way I pick ZK is that this is greater than, oh sorry, I need a 1 over square root 2, 1 over 4 square root 2, sum over everything. And there you have it, there was my inequality. By the way, I realized I made kind of a mistake. One of the quadrants has to satisfy this with the absolute value on the inside. If you look over the notes, this is pretty clear. Okay, so let's see how much time we have left. Okay, so now, main theorem I wanted to prove today, if mu is a complex measure on, I can't even write it, but on a sigma algebra, then this is finite. In other words, the total variation, or you can even call it the modulus of mu or absolute value of mu, but the total variation of mu is a positive finite measure. Okay, so proof. So first thing, note that if mu e, and by the way, with this proof, you really see the lack of the positivity, the lack of this monotonicity that you have for positive measures. Positive measures, if I have a subset, if I have a subset of B, the measure of A needs to be less than the measure of B. You lose that when you switch to complex measures, and you really see that rear its ugly head in this proof. This would be so easy if we had a positive measure, but we don't. So we're going to use this. So first off, let's just note what happens if I have a set. I'm going to prove it by way of contradiction. I'm going to assume that this is infinity, and then I'm going to derive a contradiction. But first off, if this happens, so say I have my total variation measure being infinity. Well, then I'm going to set t, and here's where you see something very strange happen, but this is just that lack of positivity. this is still finite. That number is still finite. This is a finite number, but the total variation somehow, when I chop up everything and I take the soup, I get infinity. Okay. So if I do that, then let's see here. Well, t is less than infinity in particular. And so there exists, by the definition of this, I'm taking something less than supremum. And by the way, that supremum's over an infinite set, but you can actually do a finite set. That's going to be on the final, but for this, it's really easy. So there exists E1 through EK disjoint, or sorry, let's write En, such that this is greater than t. Okay? All right? By the lemma about complex numbers, so each one of these is a complex number, there exists a subset of 1 through n such that I can pull the absolute values out for this subset. Okay? Oh, and by the way, I get actually here a 1 over 4 square root of 2 t. Okay? And if you look at the way t is defined, this is actually equal to 1 plus mu of e. Okay, so let's look at a few things. So what I'm going to do is I'm going to take the union of these EKs for K and S, and that's going to be a set I'm going to call A. So we'll let A equal the union K, S, EK. Then what happens is this just gives me the measure mu of A. This is greater than 1 plus measure mu of E. Okay? Notice that's greater than or equal to 1. That may be 0, but that's greater than or equal to 1. And what else if B is equal to E minus A is a subset of E, then the measure of B, this is the measure of E minus measure of A. So one thing, this is just a definition of the complex measure. You can subtract it. By the way, we don't even need to worry about subtracting infinity because everything's finite. This is greater than mu of E of A. And now that is greater than, so I'm going to do something really weird here. Made a mistake. Actually, I can interchange these because it's got the absolute value around it. I can do that. This is the lack of monotonicity rearing it out of the head. And now here, this is greater than 1 plus E minus mu of E, which is equal to 1. Okay, moral of the story is the following. If this equals infinity, then I can split it up. So I can split it up into two measurable sets such that both of these things are greater than 1. And one other thing. Since E is the disjoint union of A and B, and this is a measure that's infinity on E, one of these things has to be infinity. So i.e., without loss of generality, I can assume that U of A equals infinity. Okay, so I remind you, this little trick I did here, normally you would, in fact, it was so weird for me, normally this, you think of this as the bigger measure, right? A is contained in E, not necessarily for positivity, so what I did was I switched these, which you can do inside absolute value or modulus, and I wrote it like so. Okay, now, what do I do with that? Now, by way of contradiction, assume that this equals infinity. Then what I can do is we get disjoint sets A1 and B1 in M disjoint such that what happens? Well, let's say mu A1 is infinity, measure of A1 and the measure of B1 are greater than 1. Okay, and now we just iterate this process. So now this is another set that has total variation measure infinity, and then we get a sequence. So you do the same thing on that, and then you do A2. So what do we get at the end of the day is get a sequence A1, A2, etc. with mu AK equal to infinity and B1, B2, so here, disjoint with mu of BK greater than or equal to 1. Why are they disjoint? Well, all of these things are disjoint, and I perform the procedure in each one. And so this is a problem, but we have that mu is still a complex measure, so it's union. This should be a complex number, but on the other hand, this should split up like so. And now, no modulus, no absolute values. These should all be complex numbers. This has to be a convergent series, but a convergent series, even of complex numbers, the general term has to go to 0. If that doesn't happen, this is a contradiction. This is greater than 1. And in other words, this was the problem. You've got to have a finite measure. So we're kind of running out of time here, but let me mention one last thing, and then we'll get into absolute continuity and towards the radon-Nikodym theorem on Friday. Next week, I'll prove the duality of LP spaces and maybe just kind of wrap up some odds and ends, and then we'll be done. So one last thing. Let Mx be the collection of complex measures on a measure space X. Really, the measures are on the sigma algebra. A lot of people will write in the sigma algebra. That's what actually plays. It's all you need, actually. But then what we can do is we can define a norm on this. Is a norm on MX. So it's very easy to prove that it's a norm. Oh, by the way, this is definitely a vector space. If I add up two complex measures, I naturally get another complex measure, scalar multiples. Everything's fine. This is a norm. Why is that? Well, the triangle inequality is basic. You can check that. It's really easy to check that. Say I have two complex measures and set E, this is going to be less than. You just look at the definition, and when you take X, that's exactly what you have. That's easy to do. Triangle inequality is fine. The scaling is fine if you look at the definition of this total variation constants pull out. The fact that it's 0 if and only if the measure itself is 0, well, notice that for any complex measure, this is less than that. And so, in other words, if this thing is 0, then this will be this. Now, see, we can use monotonicity because this is a positive measure. That, if that's 0, then these are 0 for all E. That's 0 for all E, and hence the measure itself is 0 measure. Okay. So anyway, that's a norm. Turns out it's actually complete with respect to this norm. I don't have that in the notes. There's some proofs of it. It's kind of a pain, and we don't have time for it. But if you're interested in it, you can shoot me an email, and I can kind of point you to the right place to look to see why that's why it's complete. So it turns out this is a Banach space. So pretty cool. All right, guys. So I'll be around this afternoon for office hours. Look for the Zoom link soon, and I will see you all Friday.